In this video, we're going to look at freezing point depression and boiling point elevation. These are some kind of interesting properties that occur when you start looking at what's happening to the particles in a solution as you either try to freeze the solution or boil the solution. So first, this freezing point depression. It says here that in a solution, the solute particles interfere with the freezing process, making it more difficult for the particles to align in a rigid, solid structure. Okay, so let's say I've got water, pure water, and I want to freeze this pure water. And water is kind of interesting as a solid. It has a very specific organized crystal pattern where these water molecules align very specifically in this organized pattern. Water molecule, water molecule, water molecule, more water molecules that are all in this frozen solid state. There's an ice cube. Well, now we know that in a solution, let's say it's salt water, sodium chloride dissolved in water, the sodium chloride will dissociate so that really you've got three particles swimming around in the beaker. You've got water molecules, but then you have individual sodium ions and individual chlorine ions. And we know that they're kind of attracted to each other in a way that if this diagram is kind of showing like a water molecule, how it's got this positive end and negative end. And the positive end of a water molecule would be like the little baby hydrogens. And this negative region would be like the big oxygen. And those water molecules are attracted to the oppositely charged ions in the solution. So maybe this purple ion is kind of like a positive sodium ion or something like that. But the problem is then that I've got these other particles that are interfering with this crystallization process. That really, in these nooks and crannies, I've got little like sodium ions. Maybe these are like positive sodium ions that kind of interfere with the alignment of these water molecules in this perfect rigid crystal pattern. And then kind of similar, maybe now I've got like these negative chlorine ions that get into the nooks and crannies and make it harder for these water molecules to align in this perfect repeating crystal pattern. So what happens then to the freezing point? It becomes lower than what you might expect. More energy will need to be removed in order to freeze the liquid. And so I've got to remove more energy in order to align those perfect particles in this lovely repeating pattern of crystallized water molecules. That results in a lower freezing point. So for example, we know that pure water freezes at 0 degrees. Well, now if it's a solution of like salt water, it's going to freeze at a lower temperature. So hence this freezing point depression. The freezing point is depressed, it's lowered. So here's why we put salt on the roads in the winter. Well, for a couple of reasons, but one of them is this freezing point depression, that if I put sodium chloride or calcium chloride, whatever kind of salt we put on the roads, usually kind of a mixture of different chlorides, when those sodium chloride or calcium chloride molecules dissolve in the water, it kind of, again, prevents this freezing process. So instead of water forming ice at 0 degrees, now we might not see ice form until maybe -10 degrees, maybe even lower than that. Now, you'll also hear the weathermen say, on these really cold, crazy cold days in winter where the air temperature is well below 0, they'll say, yeah, it's too cold for salt to work on the roads. Well, that might mean then that the air temperature is below the new freezing point. So instead of water freezing at 0 degrees Celsius, which usually we think about Fahrenheit for our outdoor temperatures, but in the Celsius metric world, let's pretend, it's 0 degrees Celsius when water starts to freeze. Well, now it might not freeze till -10, -15. But if the air temperature is below that, now it is cold enough for ice to form. But there's your freezing point depression. In a solution, the freezing point is lower than the freezing point of just the pure liquid, the pure solvent. Boiling points are elevated. Boiling point elevation means that the boiling point of a solution is higher than just the pure solvent. And again, it comes from this attraction of particles now that are in with the water. And so let's say, again, it's a solution of maybe salt water, sodium chloride mixed in with the water. And maybe, again, this is like my positive sodium ion, this purple ion in there. And we know then that water molecules will be attracted to that positive ion. And it's the negative oxygen end of the water molecule that would be attracted to the positive ion. And we could say the same thing about the negative chlorine ions, that then the positive hydrogen end of the water molecule would be attracted to a negative chlorine ion in solution. But again, now in this new solution, we've got all these extra attraction. We've got these extra attractive forces. So, I mean, boiling is all about separating the water molecules from the liquid phase and then creating this vapor, this gas phase. Well, if I've got all this extra attraction in the solution because I've got these oppositely charged ions that create attraction with the water molecules, now I'm going to need to increase the temperature even more to separate those water molecules from the solution and then eventually get them up into the gas phase. And so if I have to add more energy to separate those water molecules from the liquid phase and then get them off into the gas phase, I need to separate those water molecules from those ions that are in the solution. I'm going to need a higher temperature. So boiling points are elevated. One of the reasons why they say you should add like a little sodium chloride, a little salt to, let's say, your boiling pasta water or something like that. Now, obviously, part of it is for flavor, but it also makes the water boil at a higher temperature so that by the time the water is boiling, instead of it being 100 degrees Celsius, it might be 105, 110 degrees Celsius, depending on how much salt is in your water, which then, if the water is already at a higher temperature, it'll cook your pasta faster and obviously add flavor. So anyways, these are two things that we can definitely look at in the lab, and we can compare the freezing point and boiling point of a pure solvent to that of the solution. Freezing points are lowered, boiling points are elevated.